Welcome all. Welcome to class 45 of CS. We'll start with moving average process, but we'll go to ARMA classification. So let me start with the first example, that is MA1. How MA process looks like. MAQ we write, MAQ. So here we talk about the number of parameters, MAQ here. So if I want to write XT in terms of the average value, theoretically I'm saying, and we have to estimate it from the sample, that's a separate thing. Mu cap, mu hat will come then. Now XT, at any time t, if you want to know the value of the process, any process you are considering, any time series process, any stochastic process, you want to know the value at t, you can express XT in terms of its average value, and this will be estimated value. When you estimate this one, mu plus whatever values you get, you take the average, okay, that way. So this is population average here, but from the data when you do, you have to estimate it. That's a separate thing. Then instead of taking alpha xt minus 1 minus mu, will not try to make it dependent on its previous values here in MA process. Instead, we'll start writing this way: beta 1 et minus 1, and then beta 2 et minus 2. This is the random shock at time t minus 1. Random shock at time t minus 1. That means whatever you must have estimated before one step and whatever originally you got, the difference you need to take. Similar to this one. Let me insert one line here. Suppose we are here, this is time t minus 1, sorry, and you need to estimate the value here, okay, xt at time t. You need to estimate the value here, the value of the process, whatever process you are considering. Then that will be the average of this, because we are here already, we know the values of the process. So we know these values, x1 to xt minus 1. The average of the process you take anyway, then plus extra, you give a weight to et minus 1. Et minus 1 means whatever you must have predicted here, okay, the prediction at this point, t minus 2, here one step prediction you must have predicted here, and you observe one value, that is the real value, xt minus 1. You predicted here for one step, similar to what we will be predicting now here. From here, we know the value here, we have to predict here. Similar to that, you must have predicted, if you predicted, I'm saying, the value here, otherwise it's difficult to know the errors, okay. You must have predicted some value, you must have observed the real value, okay, the real world value, whatever way it must have happened, you find the difference, that is et minus 1. So it's a linear combination. Once again, we'll take q such innovations, q such random shock, white noise, whatever you say. So we'll go up to q et minus q and et. This is the formula for MAQ. Now in terms of differences also you can write, if you denote xt minus mu as yt, then yt will have a simpler form. Just you can write beta 1 et minus 1, beta 2 et minus 2, then up to beta q et minus q plus et. So this is yt is equal to this. This is your MA process. We can write this way: beta 1 et minus 1, beta q et minus q plus et. This one you will get. However, we would like to write in a different way here. Xt minus mu, I can write this is equal to beta 1. This could be beta et. Beta et is et minus 1. Then b et. Then b square et using the symbol we know already. And this will be equal to bq et plus et. Then if you take everything common, you can write xt minus mu is equal to, you take common, beta 1 you have, et will take common, beta 1 b, beta 2 b square, that way. So if you take et common, you will get 1 here. Let me write 1 here. 1 plus, from here I will get 1 if I take et common. Then from here beta 1 b plus beta 2 b square. Then beta q bq. If you see this, this is a polynomial. This is a polynomial of order q. Highest power is q. So this also you need to remember. This is the general representation. Okay. So this will be any function. If you want, you can write fb this way also, not a problem. But we'll follow the symbol as well. Theta b, it's a function of b. It's a function of b et. So xt minus mu is equal to theta b et. This one for MA process. This is for MA process. Okay. If I write it 1, this is for MAQ process. Similar to, we had one for AR process. Okay. For ARP process, if you remember, we had one representation. Okay. You remember that? xt, how it was AR process? xt is equal to mu plus alpha 1 xt minus 1 minus mu up to alpha p xt minus mu plus et. This was there. And then we took xt minus mu here. And then we took this one common, right? Beta, this is beta b, you can write b xt minus b mu. So alpha 1 b, if you take common, you get xt minus mu. Even you get everywhere xt minus mu. But it will be alpha p bp xt minus mu plus et. So if you take xt minus mu common, okay, here also you will get xt minus mu. You take everything to the left hand side, you can go through previous videos, and in that case what will happen? 1 minus alpha 1 b you will get. Okay, if you take xt minus mu common, you will get 1. Let me write here. You have to bring everything to this side. Xt minus mu minus this is equal to et. That way you take xt minus mu common, you will get 1 minus alpha 1 b minus alpha 2 b square minus alpha p bp. Okay, that is, I can write here also xt minus mu 1 minus alpha 1 b minus alpha p bp. Okay, this is equal to et. This was there. So we'll replace this one by another function. I think I've written already theta b for that. If you want, you can change now that one. Phi b, it's a function of b, is equal to right hand side you see et. So this is the representation for ARP process. Now we'll consider the general process, which is ARMA, ARMA PQ. Let me write ARMA PQ. ARMA PQ process, how you need to write. This one you can write 2. If you write the general PQ process, you start writing the average value plus alpha 1 xt minus 1 minus mu. Then alpha p xt minus p minus mu, you have to write anyway. Then et will be same for both. Then beta 1 et minus 1 up to beta q et minus q. Will not write et anymore. This is common to both the process. This is ARMA PQ. We have p here, alpha 1, alpha 2, alpha p. These are the parameters of ARP. And then beta 1, beta 2, beta q. These are the parameters of MAQ. And if you combine, you get ARMA PQ. P from this type, AR type, and Q from this type, MA type. Then you take mu that side, xt minus mu, and then we'll write here alpha 1 b. You take b common, that means b, this is an operator, right? This operator, if you apply to xt, it will be xt minus 1. Similarly, b mu will be equal to mu here because it's a constant. Similarly, you continue writing alpha p bp, this will be xt minus mu, and plus here also you apply the operator beta, sorry, b beta 1 et, then b you can write bq beta q et, that's all. Et will remain the same, and then what will happen if you take xt minus mu common? If you take xt minus mu common, you take everything this side, you get 1 minus alpha 1 b minus alpha 2 b square minus alpha p bp. In the left hand side you write xt minus mu, and in the right hand side you write this. Here you can take et common. Okay, so if you take et common, you get 1 plus beta 1 b beta q bq et, and then I can write this, suppose phi b, it's a function of b, xt minus mu, and this will be a function of b, another function, suppose new notation. If you write phi b here, you can write theta b here, et. This one you need to remember, this is the general process. Sometimes you get questions directly like this. So although students know how to solve a problem, seeing this one, sometimes they leave the question. Okay, so you have to remember the general process as well, but we'll not spend a lot of time here. Let's continue with the MA1 process we started last time. So we'll see the MA1 process. This will be our first example. I can directly write xt beta 1 et minus 1 plus et. I will not write the mu. You can consider this way. This is the general process, MA1 process. Mu you can write mu plus beta 1 et minus 1 plus et. You can write this xt minus mu. If you take this side, this is xt here. If you want, you can rename also like yt, it doesn't matter. So when I don't write mu to the right, remember that this xt contains mu. That means this xt is actually xt minus mu. Even if you take mu, you will not get anything extra. So that it will be easier for you to find the autocorrelation. So we'll try to find the autocorrelation. So suppose I want to find rho 1 here. Okay, I have to start with gamma 1. Gamma 1 is autocovariance between xt to xt minus 1. However, when you find autocorrelations, the procedures are different. Whatever method we must have used to find the autocorrelations for ARP, the same procedure will not apply here. There is a reason. Okay, we'll discuss about that here. So if you remember, whatever the value of xt was, we tried to put here like this, beta 1 et minus 1 plus et, and then in xt minus 1 we kept it xt minus 1, and we try to see term by term in ARP. But here you will not do that way. Here you have to put the value of xt minus 1 as well, because you don't have past process. See, this is not expressed, xt is not expressed in terms of its past values, right? It's not expressed, okay, that way. So we can find using the similar way. What we need to do here is to express xt minus 1 as well in terms of the random shock at each point. So just replace t by t minus 1 from this. If you replace t by t minus 1, you will get xt minus 1 here. You put value beta 1 et minus 2 plus et minus 1. Now if you see, in case of MA processes, it's very easy to find covariances, okay, because you have to see one by one, this one with this one, this is the first, this one with this one. If there is any covariance, that you will get from here. Okay, so this is one and this is the next. So if you try to find the autocovariance between this and this, Remember, the ET are the random shock, the white noise, whatever you say, they are uncorrelated by definition. So there is no correlation between ET minus 1, ET minus 2. That means the random shock at 2 points, they are not the same. Here, whatever random shock you have, they are not the same. That means suppose I plan to give you a 2-hour class today and 3-hour class tomorrow. Okay. So suppose I will take 2 hour, 5 minutes, this 5 minutes, this random shock. Okay. The innovation, white noise, whatever you say, that will depend on that day. Okay. During that time, what will happen? It will depend only on that time t. It has no link with the previous values or previous errors, whatever way, because in that case you can link it. Okay. They are uncorrelated. That's why we say innovations. Okay. So ET minus 1, ET minus 2 will be 0. Covariance or correlation, whatever you find. ET minus 1, ET minus 1, there will be something. We'll consider that. ET minus 2, 0. This will be 0. And ET minus 1, this will also be 0. Okay. So remains what? Covariance beta 1, ET minus 1, and then ET minus 1. All others are 0. And remember, this will be covariance of ET minus 1, ET minus 1, that is ET also, because ET minus 1 follows, you can replace T by T minus 1. This follows normal 0 sigma square. So covariance of this will be variance of ET minus 1 or variance of ET, that is sigma square. So you will get beta 1 sigma square. This is gamma 1. If you replace it by 0, okay, we'll not try to find gamma 2, because if you find gamma 2 and if you write similar formula xt minus 2 in case of MA process, here MA1 process, when you write xt here, beta 1 ET minus 1 plus ET, and then beta, you replace xt minus 2, you replace T by T minus 2, xt minus 2 you will get, that will be beta 1 ET minus 3 plus ET minus 2. Now if you check pairwise, T minus 1, T minus 3, T minus 1, T minus 2, T minus 3, T minus 2. So the more away you go from here, okay, T to T minus 2, T minus 3, T minus 4, the more distance will be among the errors. So you will not get anything. So this is 0 here. In fact, not only gamma 2, gamma 3, gamma 4, gamma 5, gamma 6, gamma 7, all will be 0 here in case of MA1 process. You will have only gamma 1. You will have gamma 0 as well. Okay. If I write gamma 0, let me replace it by gamma 0. If I write it 0, this will be T. Okay. Let me write it 0 here. And this is T now. So in that case, I will have T minus 1 here. Is it advisable to do this way? Let me do once again. Not a problem. Now let me write gamma naught here. That will be covariance xt. Okay, they are the same. So when they are the same, what will happen? Here I will write the same in both the places, ET plus here also beta 1 ET minus 1 plus CT. The cross covariances will disappear because T minus 1 T, that is 0. They are uncorrelated. Uncorrelated means what? That also, by chance, if you have any doubt, remember, these are the errors. Okay. Suppose ET minus 3, ET minus 2, ET minus 1, ET minus ET, that way. So what will happen is the distance between this and this, you travel by auto each day. Okay. We say it normally it should take 10 minutes to go from A to B. But every day it will not take 10 minutes. Some day it will be 12 minutes, some day 8 minutes. Maybe there will be an accident one day, and some other day it will rain. Okay. If you observe on some other day, there is a lot of traffic on road. So these are the different things which you have no way you can estimate before. Okay. These are the innovations, the random shock, the white noise each day. Okay. So they are uncorrelated. They are uncorrelated. So if you find correlation and covariance, that will not give you anything. Okay. So ET minus 1 ET, that is 0, ET minus 1 0. So the first term to first term, if you see here, et minus 1, you will get beta square. And the second one, et beta, sigma square you will get. So you get 1 plus beta. Here I've taken already beta 1, so let's stick to that. This one you will get. Okay. So let me write all here. Gamma naught I got 1 plus beta 1 square, and then sigma square. Then gamma 1 I got beta 1 sigma square. Gamma 2, if you find, you will get 0. Gamma 3, you will get 0. Gamma 4, you will get 0. It will continue. Even if you consider Ma2 process, this is Ma1. If you consider Ma2 process, in Ma2 process, you will observe gamma 0 will be something. I'm not writing that here. Gamma 2 will be something. But from gamma 3, gamma 4, gamma 5, all will be 0. Okay. So what will happen? You will get only values here. After 2, all covariances will be 0. And in that case, if you find rho 3 here, that will be gamma 3 divided by gamma naught, that will be 0. Rho 4 will be 0. Gamma 4 by gamma naught, that is 0. Rho 5 will be 0. Gamma 5 divided by gamma naught, 0. So in Ma2 process, remember, in Ma2 process, the autocorrelations after the third stage onwards, all will be 0. And we'll use this one, okay? When you forecast something, we'll use this one. This is a very important concept. We'll draw the autocorrelations for MA process, probably in the next class. Here, if you see, after 1, if you find, suppose rho 2 here, gamma 2 divided by gamma naught, that is 0. Rho 3 will be gamma 3 divided by gamma naught, that will be 0. Rho 4 will be gamma 4 divided by gamma naught, that will be 0. So after stage 2 onwards, all the autocorrelations will be 0 if it's a MA1 process. If it's a MA2 process, all autocorrelations after stage 3, including 3, will be 0. If you take MA5 process, you will have only 5 autocorrelations. Okay. So now find at least rho 1 here. If you divide these two, you will get rho 1. Rho 1 will be, if you cancel sigma 1, sigma square both the sides, it will be beta 1 divided by 1 plus beta 1 square. Okay, this is what you need to remember. And this is very important. The MA process is always stationary. So what will check in MA process and why will check that? MAQ, for MAQ will check for invertibility. Invertibility means what? We'll check whether MA process is invertible or not. But this is always stationary. We'll not worry about the stationarity of MA process. This is stationary because we can also find, we can check the correlations, all that, variance, mean, constant, all those things we can do. But remember, simply you can say it's a combination of the random shock or errors. So there is no way you can establish link. Okay. So this is stationary. MAQ is always stationary. However, when you talk about AR process, ARP is always invertible. We'll see that. Okay. We'll see that. Just remember now, it's always invertible. What is invertibility? We'll discuss now. And in ARP process, we check whether this is stationary or not. We check for stationarity. So invertibility is something you can say that is not very important for the analysis, but yes, you will see in some places will require that as well. So ARP is always invertible. For ARP, you need to check for stationarity. Now, if you talk about ARMA PQ process, okay, if you talk about ARMA PQ process, we'll say about this. Suppose I write ARMA PQ here, ARMA PQ, okay. We are checking for stationarity. We'll not do anything for the Q terms, okay. We'll only see whether the AR part is stationary or not. We'll do some problems and we'll discuss more. But remember, whatever method we had to check for stationarity, this one for stationarity, in AR1, if you remember, alpha more less than 1 condition was there. The same kind of a condition will come here in MAQ. So when you check for invertibility, beta or beta 1 mod, that should be less than 1. And whatever conditions we had here, we don't have derivation to check for stationarity. Similar conditions are here to check for invertibility of MAQ process. We'll see those taking some examples. We'll have some examples, and through those examples, we'll see how we can check for invertibility for MAQ process and stationarity for AR process. Okay, and then we'll see what is invertibility as well. Now, suppose I'll write a question. The first question will be about the stationarity. Okay, then we'll write the invertibility part, or we can write invertible problem because it's MAQ. We'll go to ARMA later. So the example is this: xt is equal to 1 plus et minus 5 et minus 1 plus 6 et minus 2. Now, if you see this one, you know that it's a MA process. It's a MA process, pure MA process. There is no AR part here. Though you can write ARMA, but it's a MA process, pure MA process. You see here 2, so MA2 you can write, MA2 process. If you want to classify as ARMA, you can write ARMA as well. You can write this as ARMA 02. So ARMA 02 and MA2, they are the same. There is no AR part here. So you can check for invertibility. This is always stationary. I can write check for invertibility, whether this process is invertible or not. Check for invertibility of the process. If I give a MA1 process instead, like this, I can write xt is equal to anything here, that is mu plus beta 1, et also I have to write, then I have to write beta 1, I can write anything. Suppose I will write 2 here, another 2 here, or maybe I will not write the first one. It doesn't matter. I will write 2 et minus 1 and then xt 0.5 half et minus 1 plus et. Okay, I will write this. This is MA1 process. So both are stationary. We'll not check for stationary. We'll check for invertibility. See, this is invertible, half mod less than 1, beta mod less than 1, or beta 1 mod less than 1. If this is less than 1, again remember, we are using this. We are not proving this one here. If you have a MA2 process, you can say that the coefficients are less than 1 or greater than 1, then this is invertible. You have to find the characteristics polynomial, similar way. Okay, it's similar to AR process, so I'm not repeating once again. We'll do this way. We'll write the characteristics polynomial. What is that? Remember, xt you can write this way, or xt minus mu you can write this way always. You take 1 minus 5b plus 6b square et common. From this one you will get your characteristics polynomial. So replace b by z. Okay, 6z square. You have to equate it to 0. Instead of checking the coefficients are less than 1 in absolute value or not, which is true for MA1, you have to find the roots of the characteristics polynomial, similar to ARP when you are checking for stationarity. So here you will get 6z square minus 5z plus 1 is equal to 0. I don't think here the roots will be greater than 1 in absolute value. So you can check it. If I'm not wrong, you will get the roots 1 by 2, 1 by 3. This looks like, okay. So they are not greater than 1 in absolute value. If you draw unit circle, okay, if you find the roots, they must be outside the circle. Even on the circle is not allowed. So 1 by 2, 1 by 3, if you write on x-axis, this is 1 by 3, this is 1 by 2. Okay, 1 by 3, 1 by 2, they are within this one, radius 1, unit circle. So this is not invertible. MAQ process, this MAQ process is not invertible. Okay, this is not invertible. Let's go to ARP process. Now this one, if you consider this one, even here also you can find the characteristics polynomial. In this case you will get 1 minus 2b is equal to 0, b will be equal to 1 minus 2z, z will be equal to half, In this case, you will get 1 minus, I'm talking about this, okay, this type. 1 minus half z will be equal to 0. So z will be equal to 2. It's greater than 1 in magnitude. Okay, so this is invertible. Instead of doing that, if it's MA1, directly you can take the coefficient. Okay, this is what I've written, the condition. If you want to use the general formula, you can do that. It's similar to AR1, so I have not written formally here. Okay, so this is over now. But still, we'll keep this because we'll use these two once again. There is a difference. Okay, one is invertible, one is not invertible. This is not invertible. Both are stationary. This is not invertible, but this is invertible. Okay. So if you find here rho, and if you find rho here, remember the formula for MA1. Okay. So now we have rho here. Both are MA1. Okay. When both are MA1, what will happen? Here, when you find rho here, the formula was beta divided by 1 plus beta square, beta 1 square, that way. Beta 1 divided by 1 plus beta 1 square. So if you find for this, it will be 2 divided by 1 plus 2 square, that is 2 divided by 5. How about this? For the second one, if you find, it will be half divided by 1 plus half square. Okay, that is 1 upon 4. So this will be 5 upon 4, and here 1 upon 2. Then if you take that one here, okay, you will get 2 upon 5. They are the same. So autocorrelations are the same, but one is invertible, one is not invertible. Okay, so you get the same autocorrelations for two different processes, but one of them is invertible, one of them is not invertible. Anyway, so for the uniqueness, if you want uniqueness, okay, you have to use invertibility. That is one of the reasons. Invertibility is a mathematical concept. Okay, I will go to that towards the end of this class, but let me do one example before going to the little bit theoretical counterpart when it comes to invertibility. Okay, so you can check invertibility of MAQ process similar to whatever way you used to take for the stationarity of ARP process. Okay, they're similar. You need not learn anything separately. Now let me give one example for ARMA process. You need to check whether ARMA process is stationary or not. And sometimes you will get question, you need to check whether ARMA process is both stationary and invertible or not. Both things you are supposed to check. Okay, so remember, you might get a question where you will get both the parts. Okay, MA part and stationary part. So that one I'm writing here. You need to check whether this process I'm writing here (11 ET minus 1 2 ET minus 2). Okay, so we have never seen coefficient here. This is the question. You have to check whether this process is both stationary or invertible. Check. Okay, both stationary and invertibility. Okay, check. You have to check it. Check whether this process is both stationary or invertible or not. So you are checking for invertibility and stationarity of this process. Now let me write the name of the process. What is this process? This process is ARMA. This is a ARMA process. and you have to write the components also. How many parts from AR and how many are from MA? How many AR you have? 1, 2, 3, up to 2. Here also up to 2. So this is a ARMA 2 process. When you check for stationarity, we'll consider the AR part. Okay. When you consider for invertibility, we'll consider the MA part, because there is a chance that MA part is not invertible. AR processes are always invertible. Again, we'll do that today after this example. AR processes are always invertible. So in AR process, AR parts, you have to check for stationarity. MA processes are always stationary, so you need to check for the invertibility of MA part. Okay. So before anything, let me write this way, 12xt. Let me bring all to this side, 10xt minus 1 plus 2xt minus 2. This side you have to bring, and you keep all other this side. Okay. And I'll write 12et minus 11et minus 1 plus 2et minus 2. Then you need to write in terms of b. It will be 12 minus 10b plus 2b square xt this side, and here 12 minus 11b plus 2b square et. Okay, this way. And if you see the next step, this part you have to check for xt minus mu. That way there is no constant term here. Normally you get xt minus u. This is a function of b, this is another function of b. This part will take and will check for stationarity, and this part we need to check, and we have to check for invertibility. Okay, this part 12 minus 11b plus 2b square, this part. Okay, and we'll replace b by z here. We'll replace b by z here. This will be our characteristics polynomial in these cases. Now this is equal to 0. Okay, so 2 comes in both the places. That is by coincidence, will not worry. So here I have the roots both greater than 1 in magnitude. Okay, in absolute value. So there is no problem from this part. Okay, the roots of the characteristics polynomial we have taken here, they are greater than 1 in absolute value. So there is no problem. The AR part, okay, we have considered, and AR part is stationary. AR part is always invertible, will not worry. Now consider the MA1. If I write this way, if you add, you will get 11. If you multiply, you should get 24. 24, right? 12, 2. You will not get 6, 4, 10. So how can you get 11? If you don't have any clue, you can apply this. 11 minus b, 121 minus 4ac, 96. Okay, divided by 2a, 25 we got. Okay, so 5, 11 plus 5, 16 divided by 4, 11 minus 5, 6 divided by 4. Okay, so this is 4 and this one is 3 divided by 2, 1.5. 4, 1.5. 25, right? 21, 25, 5. If you subtract 5 from 11, you will get 6. 6 divided by 4. Yeah, that's fine. 4, 3 by 2. So these are again greater than 1 in absolute value. Okay, then what will happen? This side will be invertible. So this process, this ARMA process, ARMA 2 process is both stationary and invertible. Okay, now let's check what is really invertibility, because we talked about stationarity before. We'll talk about invertibility in this class. Okay, and we'll end this class. Now consider the MA process. Consider MAQ process. Okay, if you have a MA process, you have the general expression you need to write. If you have the general expression from for MA process, then you can turn the sides. Okay, let me write MAQ as this, or we'll start with MA1. It will be easier. MA1 process, let me write this one. xt is equal to mu plus, I can write, instead of beta 1, I can write beta, because we have only one term, beta et minus 1 plus ET. This is MA1 process we considered when we started the class. Okay. So if this is your MA1 process, if you see the expression, we have expressed this one MA1 process in terms of only the errors. We don't have any past dependency when it comes to the process itself. Now we want to see whether we can invert or not. Invertibility is a very interesting and very useful, at least in theoretical, useful concept. Okay. Once you know whether this, if this is invertible, then this is going to help you. Because invertibility, if you have, at least you will get the autocorrelation processes. I mean, we saw two MA processes. If you remember, I took the coefficient half and 2. In both the cases, we had the same autocorrelations. We don't want that. Okay. So we'll see what is invertibility here. Xt minus mu will find, and we'll take common similar way. Xt minus mu, you take common, you write b et. Okay. So you'll get beta b plus 1 et. And then xt minus mu will be equal to okay, let me write this side so that I will be able to express et in terms of these. So it will be 1 plus beta b, you take that side inverse, and you get xt minus mu. Also remember this simple formula, 1 plus x inverse. Okay, 1 minus x inverse. Here you get all the terms positive. Here 1 minus x plus x square alternatively will get. So we'll use those. We'll use that. Et will be equal to 1 minus beta b plus beta square b square. That way it will continue. Xt minus mu. And then Et will be equal to, you can multiply this one. Okay. So xt minus mu you will get anyway. Then beta b xt minus mu. Okay. So term by term, if you write, you will get all this because the mu is there. Okay, this side, that mu I have written here. So that way you will get this one. Okay. What is b of xt minus mu? What is b of xt minus mu? Let me write first. Xt minus mu minus beta. What is b of xt minus mu? B of xt is xt minus 1, because we don't want any operator. B of mu is mu, that way. Then plus beta square b square xt minus mu. Xt minus 2 minus mu. It will continue. Okay, it will continue. So xt minus mu minus b xt minus 1 minus mu minus b square xt minus 2 minus mu and all that. Now this will be possible. You inverted this one actually. That's where the name invertibility comes. This is possible. Remember, this is not possible every time. Okay. This is possible only when beta mod is less than 1. Otherwise it is not possible. Okay. So this is this invertibility. This is possible. This expression, this expansion is possible. Not always. Only when x mod less than 1. Suppose I will take x2 here. You can write this one. 1 plus 2 inverse. You can write, or maybe 1 minus 2 inverse 1 plus 2 plus 2 square. You can write. This will not be true. This is actually minus 1 power minus 1. That is 1 by minus 1. How can be sum of all positive number and negative 1? This is possible only when x mod less than 1. Similar to this one is possible only when beta mod less than 1. So we try to invert it. Okay. So when you try to invert this one, instead of expressing the process in terms of the error, okay, we try to get the error in terms of the process. And if you go further and you try to know a bit about this, this is quite amazing. But anyway, theoretically, because we have infinite terms here, we'll not use it practically, but theoretically, if you try to understand this one, okay. Remember, we always said it is innovation, it is random shock, it is something which is not, which can never be derived from the past of the process. But you see, ET can be expressed, okay? ET can be expressed in terms of past of the process. Xt minus 1, xt minus 2 is here, xt minus 1 is here, xt is here. At least theoretically, ET can be expressed in terms of past processes, okay? Whatever values you have by now, using those values, you can find ET. Theoretically, I am saying. But see the number of parameters, the number of terms, mu, all these things, estimation, it's quite quite problematic. So you should not worry about that. But invertibility here means whether you will be able to invert the process or not. Normally, XT is expressed in terms of the past errors, but whether you can express error in terms of the process or not, that is what you wanted to see. And in that case, remember, you need the concept of invertibility. And the process to check invertibility for MA process is similar to the process when you check for stationarity of AR process. Okay. So MA process is always invertible. And remember, AR process is always, MA process is always stationary. So we have to check always the invertibility of MA process. However, AR process, if you try to invert, you will get some result. AR process, when you see, AR process is always invertible. We'll take that one as well. And then we'll end the class. Okay. So consider ARP process. We always check for stationarity. We never check for invertibility of ARP. So if you remember ARP, we wrote this way, ARP process, the general one, xt is equal to mu alpha 1 xt minus 1 minus mu alpha p xt minus p minus mu plus et. This was ARP process. And from this process, if you write this alpha 1 b xt minus mu, because b xt is xt minus 1, b mu is mu, similar to this alpha p bp xt minus mu, okay, plus et, and you take all to the left hand side. The polynomial you will get alpha 2 b square alpha p bp xt minus mu, that is et. Okay, and for this one you have to give a notation. We have given some notation, I don't remember, but yeah, today we consider 5b xt minus mu is equal to this. Okay, this is your normal notation. Now if you consider AR1, then P will be 1 here. Okay, here P, if you put 1, will get only 1 minus alpha b. 5b will be only 1 minus alpha b. You check this one, you put P1. Okay, for AR1. So it will be 1 minus alpha 1b or alpha b, if you want, you can write, because there are no more alpha 2, alpha 3 here. Xt, you can write minus mu, that is equal to et. Okay. Now what will happen when you try to take this one right hand side, and if you express, because alpha mod less than 1 already here, you can take this one and express xt in terms of errors now. Okay, it's the opposite part. Suppose I'll write xt minus mu, and I will take 1 minus alpha 1b inverse et, and then what will happen? The opposite way. We'll try to write in the MA way. Okay, so you apply here 1 plus alpha. Alpha is better because only one term. Why to write alpha 1? Let me write alpha. So here you have alpha b plus alpha square b square. That way you write. Then what will happen? This will be m plus. Now considering that this is alpha mod less than 1 again. Okay, stationary. So now if you consider this one, 1 plus alpha b square et, this will be et plus alpha b et minus 1 plus alpha square et minus 2, that way. Now see, you express xt in terms of the errors and the average value. This looks like MA process. This looks like MA, right? So from AR, we can express AR1 in terms of MA. But the problem is, the representation is MA infinity. Again, it will be very tough. Okay, we can't utilize this one. Only for theoretical academic value, I'm saying. Theoretically, whether you can express this one or not, for that, we are inverting and we are seeing whether that kind of a thing is possible or not. Okay. So this will also be not useful in problems and useful in practice, but only for knowing, for understanding, and for academic interest, I express this way. We'll continue with the problems next time.